We've talked about Taylor polynomials earlier, but we really talked about a very specific type, and that was Maclaurin polynomials. And that's the kind that are centered at 0. If you remember, to be centered somewhere basically means that's our starting point. We're going to make sure we're perfect at that point and try to be as accurate as we can at points around that area. But then the farther away you get from the center, the worse off the estimation is. Because the whole point of a Taylor polynomial is you're using a polynomial to estimate the function, some other type of function. That could be e to the x, sine of x, natural log of x, things like that. So here's the general form. It's very similar to the Maclaurin one we've already gone over. The only difference is instead of f of 0, f prime of 0, f double prime of 0, it's f of c, f prime of c, f double prime of c. And this is really just the more general form. This would still work for Maclaurin as long as you plug in 0 for c. But this will work for any center. So you can be centered at 1 or at -3 or at pi or anything like that. So the only big difference is that when you take the derivatives and plug in a value, now you don't always plug in 0 automatically. You plug in whatever center they tell you. And they do always have to tell you the center. That's not something you have to figure out or come up with on your own. The only other difference in the formula is you can see that you do have to subtract your center from x. So if your center is 1, then instead of just plugging in x, x squared, x cubed, you'll have x minus 1, x minus 1 squared, x minus 1 cubed, and so on. So let's start with an example. It says find the third degree Taylor polynomial for f of x equals e to the x centered at 1. Well, just like with Maclaurin series, or Maclaurin polynomials, excuse me, the degree tells you how many derivatives to take. So this would be the first derivative, second derivative, third derivative. Obviously all the same. Now centered at 1. So this time, because we're centered at 1, we plug in 1. Well, e to the 1 just gives you e all the way down. Now our formula, again, is going to look like this. F of c plus f prime of c x minus c plus f double prime of c over 2 factorial x minus c squared plus f triple prime of c over 3 factorial x minus c cubed. Okay, so that's what we're going to be plugging into. And we're just going to be plugging e in for all of the f's because that's what we got for all of them. So we're going to end up with e plus e times x minus 1 plus e over 2 factorial x minus 1 squared plus e over 3 factorial x minus 1 cubed. And that's our answer. So again, we just plug our values into the f's. And we also, in this case, have to make sure we plug our center in for all the c's. So 1, 1, 1. Okay, next example. Find the fourth degree Taylor polynomial for y equals the natural log of x centered at 1. Okay, so we get y equals the natural log of x. Y prime is 1 over x, or x to the negative 1. Y double prime would be negative x to the negative 2, which is negative 1 over x squared. Y triple prime is positive 2x to the negative 3, or 2 over x cubed. Fourth derivative will be negative 6x to the negative 4, or negative 6 over x to the 4th. Okay, so now we're centered at 1 again, so we plug in 1 and see what we get. Okay, natural log of 1 is 0. 1 over 1 is 1. Negative 1 over 1 is negative 1. 2 over 1 is 2. Negative 6 over 1 is negative 6. Okay, so again, the general formula for what we'd be doing here would be f of c plus f prime of c x minus c plus f double prime of c over 2 factorial x minus c squared plus f triple prime of c over 3 factorial x minus c cubed plus the fourth derivative over 4 factorial x minus c to the 4th. Okay, so now let's plug in the values and see what we get. So 0 goes in for this first term, so it really just disappears. So then we plug in 1 for here, so 1 times x minus 1. No, you don't have to write that 1 out front if you don't want to. Plus negative 1 over 2 factorial x minus 1 squared. Plus 2 over 3 factorial times x minus 1 cubed. Plus negative 6 over 4 factorial x minus 1 to the fourth. Okay, so just keep in mind the negatives you could change to subtraction if you wanted. So for example, this right here could be changed to minus 1 over 2 factorial if you wanted. Or right here it could be minus 6 over 4 factorial. That would be fine. Also, it is possible to reduce some of those fractions. I would say for my test, if it's just open-ended, just leave it exactly as it is. I'm pretty confident you know how to reduce fractions. If it's a multiple choice question, though, just make sure you're looking closely at whether they have reduced those fractions, because that could be why it's looking different than yours. Final example, find the third degree Taylor polynomial for y equals sine of x centered at pi over 2. So we need to find up through the third derivative. So y equals sine of x, y prime equals cosine x, y double prime equals negative sine x, y triple prime equals negative cosine x. Alright, so now we need to plug in pi over 6. Now since we're centered at pi over 6, we have to plug pi over 6 into all these functions. So sine of pi over 6 is 1/2. Cosine of pi over 6 is square root of 3 over 2. So that would make it negative 1/2 here and negative square root of 3 over 2 here. Okay, I think we've worked enough with the general function. I'm just going to skip straight to the answer, so you don't have. I'm not going to rewrite the general formula here. We'll have 1/2 plus square root of 3 over 2 x minus pi over 6 minus 1/2 over 2 factorial x minus pi over 6 squared minus square root of 3 over 2 over 3 factorial times x minus pi over 6 cubed. So just to give an example of one where we would reduce the fractions, or where just what it would look like if we did, let's look at this one. We'll have 1/2 plus square root of 3 over 2 x minus pi over 6. Okay, 2 factorial is 2, so that'll become 1/4 x minus pi over 6 squared minus 3 factorial is 6, so that should end up being square root of 3 over 12 x minus pi over 6 cubed. So that would be the third degree Taylor polynomial for sine of x centered at pi over 6. Again, what we're doing here is we're using a polynomial to estimate what sine of x does around pi over 6.